Electronics designers don't reinvent the wheel every time they go to build a new circuit. Instead, we have a collection of circuit elements or blocks that we've used before and that we understand and come to mind, and we want to be able to put these blocks together to do new functions. So at this point, we're accumulating quite a number of useful blocks. Let me review some of them for you. For instance, we have the voltage divider with two resistors, R1 and R2. And maybe this is a divide by 2 voltage divider. We have the potentiometer, a kind of voltage divider, but with a wiper that can vary the output ratio. We have a display unit consisting of a resistor and a light-emitting diode. We have an op-amp that has a couple of inputs named the non-inverting and the inverting input, and it has an output. And we know how to use that as a comparator, and soon we'll be using that as an amplifier as well. We have a power supply, for that matter, a plus 5 volt to ground power supply. And what you'd like to think is that you can put these pieces together in arbitrary ways, and if they worked on their own, that they'll work in combination as well. So the rule that's important that makes it easy to put these blocks together and have them work, not change when you stick a new one on the output of an old one, have the behavior of both of them be what you expect it to be. This rule has to do with impedance, Z. Z, impedance, measured in ohms. And the way I express this rule is low Z feeds high Z. It means that you come to know the input and output impedance of a voltage divider, a potentiometer, a display unit, an op-amp. Each one has an input and an output, and you get used to, in a rough way, what are the input impedances, what are the output impedances, and then you can stack these things up so that the output of this one feeds the input of this one, the output of this one feeds the input of this one, and so on. And as long as you follow this rule, that a lower impedance feeds into a higher impedance, they will behave in a fairly predictable way. So how much lower and higher? That's up to you. It's a matter of how accurately you want these things to behave in their unconnected way, to behave just as they would have if they, on their own. It's great if you can have a factor of 10, like if something has a input impedance of 10,000 ohms. It would be great if the thing that's feeding it has an output impedance of less than 1,000 ohms. But if your ratio is 3, that's probably okay too. As it gets to be more like 1, they're really going to disturb each other and not work so well. So what are some of the input and output impedance of these things? So the input impedance of a simple voltage divider, a good version of that is R1 plus R2. That's the input impedance. And the output impedance here is just R2 itself. Okay? For a potentiometer, we can say that the input impedance is the resistance of it. And the output impedance, I don't think, because this can move and we don't really know that it's where it's going to be, I think a safe version of that is that the output impedance is also 10K. So that's kind of a conservative one. Here is an LED display, and I've given it a particular resistor to make it a certain brightness with a certain voltage, and it doesn't really have an output. It doesn't couple to anything except light, but we can say that its input impedance is, in fact, whatever resistor value I used. Op-amps are wonderful because, ideally, their input impedance are infinity, and their output impedance depends on the op-amp, and this is a little rough and ready, but a good figure here is 100 ohms. And so this is a wonderful device. It's because it has a high input impedance, you can connect it to the output of almost any other block, and it won't perturb it very much. On the other hand, because it has a low output impedance, you can connect its output to the input of almost any other block, and they'll work well together and both behave in close to their ideal ways. Finally, we have a power supply, and a power supply is supposed to have an impedance of 0 in principle. In fact, our power supply is pretty good. What does that mean for a power supply? What impedance really means is how much does the voltage change as a consequence of current changing. So Z is measured in ohms, and it's defined as change in voltage for a change in current. So in the case of a power supply, what you're saying is, I would like to measure this with a voltmeter, and it reads 5.042 volts, it says. It's supposed to be 5, happens to read 5.042. Now I put some load on my power supply. Maybe I put a 100 ohm resistor there, and I know that means that about 50 milliamps is going to be flowing. And I read my voltage again. Well, it should be 5.042, but it isn't, because it's not an ideal Z out equals 0 power supply. Instead, it reads 5.022 volts. So delta V here was 0.02 volts, 20 millivolts. Delta I was 50 milliamps. And so the impedance, which ideally would be 0 of that power supply, is delta V over delta I, which is 0.02 over 0.05, 0.4 ohms.